In the next few videos, what we're going to do is we're going to look at specific types of input to our Unity feedback system, and we're going to see what sort of requirements we need of our G of S, our open loop transfer function, in order to get desired steady state error. So in this first video, we're going to be looking at a step input, and more specifically, we're going to consider a unit step input. So I've copied our general equation from the previous video, where we had our steady state error in terms of our R of S and our G of S over here on this side. And so now, because we're considering a step input, we can say that that R of S is equal to 1 over S. And again, because we have that 1 in the numerator, we know that this is a unit step. Again, keep in mind we could have any type of gain, so we would just replace that 1 in the numerator with our gain factor k. So all we have to do is plug that into our expression, so we can say e of infinity is now equal to the limit as s goes to 0 of s times 1 over s divided by 1 plus g of s. So of course these s's cancel out up here in the numerator, and now we have just constant 1 in the numerator. We have a 1 in the denominator, and so the only thing that's going to depend on this limit of s is our g of s. So we can sort of move that to be right beside our g of s. So we have 1 over 1 plus the limit as s goes to 0 of g of s. And so this would be our expression for a step, a unit step, remember, a unit step input to a Unity feedback system. So again, this is relatively specific in terms of where we can apply this equation. Again, if we had some gain, we could change this 1 to whatever our gain factor is, k. We could deal with it that way. Okay, so now what we want to say is for specific steady state error, what sort of requirements do we need of our open loop transfer function G of S? So let's start by saying we want 0 steady state error. So we could say for our E step, so our error for the step of infinity, to be equal to 0, then we have to have our limit as s goes to 0 of G of S has to be infinity. So we have to have this limit as s goes to 0 of our G of S equals to infinity, and so that just comes from that boxed equation above. Of course, if we have 1 divided by infinity, that's going to go to 0. Another terminology thing is that this term here, this limit as s goes to 0 of G of S, is also known as our DC gain of G of S. Okay, so to get a better idea of our requirements for our G of S, let's sort of generalize our G of S equation. So remember, G of S is ultimately a transfer function. So let's generalize our G of S equation. So we can say our G of S in general is going to be equal to, now remember we can represent this a couple different ways. In this case, what we're going to do is we're going to say we have some zeros in the numerator, so s plus z1 times s plus z2, so this is our factored form, so dot 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 for however many zeros in the system we have. Now we also have some poles, so we have s plus p1, s plus p2, so all of those are multiplied by each other, however many poles we have, and then I'm also going to include this term here, which is s to the power of n, and so these are going to be poles at the origin. So what we can say then is if we want that limit to go to infinity, so for the limit as s goes to 0 of G of S to be equal to infinity, we have to have n greater than or equal to 1. So we must have n greater than or equal to 1. And so essentially what that is of course, again, we're taking the limit of this, so as our s's are going to 0, all of these z's and p's are going to still be there, unless we have something here which is 0 to the nth power in our denominator. So then we'll be divided by 0 and our G of S will go towards infinity. Okay, so sort of a couple other ways that we can say that n greater than or equal to 1. So we could instead say that as our G of S has to have at least one pole at the origin. So our G of S must have at least one pole at the origin for that E step, so our steady state error E step at infinity to be equal to 0. So at least one pole at the origin. And then we can say this a different way as well, because essentially what we're doing up here in this generalized g of s equation is we're dividing by some power of s. And so we're saying that has to be at least s to the power of 1. And so if we have 1 over s in frequency, remember that corresponds to integration in the time domain. So dividing by s in our frequency domain corresponds to integration in our time domain. So another way that we can state sort of this criteria that we need to meet for zero steady state error is we could say then that there must be at least one pure integration in g of s. So there must be at least, and so there could be more, so at least one pure integration in g of s. And so again, all three of these things are sort of saying the same thing. So at least one pure integration in g of s is saying the same thing as we need to have at least one pole of g of s at the origin, which is saying the same thing as n has to be greater than or equal to 1 with this general g of s equation here. So three different ways of saying the same thing. And so let me finish this out and say this is for that steady state error for our step response, so for e step of infinity to equal to 0. Okay, so we know that it should be greater than or equal to 1, so let's consider the case of what happens if it's equal to 0. So we can say for n equals to 0, well then if we have the limit as s is going to 0 of g of s, we don't have that solely s term in the denominator. So basically this is s to the 0, so that goes away, that's just going to be 1. And as the other s's go to 0, you can see we're going to be left with z1, z2, p1, p2, and so on and so forth. So what we're ultimately left with then is just a product of our zeros divided by a product of our poles, p1, p2, and so on. And so what we get for the case of n equals 0 is we get that our steady state error for that step response input is going to be some finite number. And so there is a slightly different figure from what we looked at for our ramp input. And so if you look on page 273 in the 8th edition, figure 7.2a shows that same type of process for a unit step input. And so it shows the case of having a finite number for our steady state error, as well as having a zero steady state error when this n is greater than or equal to 1.